All right, class, we're gonna get started. Today we're gonna have video start class off for Friday. So primarily today we're gonna talk about the Bernoulli equation. Right? So the question is what is Bernoulli for? So I'm gonna talk about limitations of Bernoulli. So here we'll look at a few different things that we can actually use the Bernoulli equation to understand. Although we will work our way to a limitation of Bernoulli, so we can understand kind of trade-off between things that are pretty well explained by Bernoulli and where we need some other theory to understand this. But we're going to start with some kind of classic demonstrations of the Bernoulli principle at work. And remember that in the absence of a change or a significant change in elevation, then the Bernoulli equation really tells us that velocity goes up, pressure goes down, right? And so that's really the basis of a lot of what we're going to see. Okay, so what we're looking at is levitation of a ping pong ball in a stream of air. So let's just talk for a second about what's going on here. So if the stream of air is pointing straight up, we actually don't really need Bernoulli equation to understand the majority of what's happening. If we doing a free body diagram on the ball here, there'd be a gravitational force pointing down, and there'd be some drag force that is actually pushing it upwards, right in the direction of the flow. We haven't covered drag yet, but we will talk about drag on objects later. In chapter 7. But we can understand that the ball is going to find some equilibrium position where that drag force is directly balanced out by the gravitation. But one question you might have here is why doesn't it move out of the stream? And we're going to see that it actually has a pretty significant effect actually holding it to the center of this stream. Stops flowing from the straw, it falls down. So this demonstration is the same basic idea, but now we have a hair dryer. So you can actually tilt the hair dryer quite an angle and still keep the ball within this fluid stream. And we can understand this using Bernoulli. So if we think about what's going on here, we have a stream of air that's relatively high velocity. High velocity meaning low pressure. And then outside of that, we have sort of ambient air at low velocity, therefore higher. And so we have this region of lower pressure created by the motion of the fluid that the ball is sitting surrounded by the region of higher. So now if the ball were to move over out of that stream, it starts entering a region of higher pressure. And that high pressure on the side of the ball pushes it back inward. So the Bernoulli equation helps us understand that this fluid stream here has lower pressure, and that's basically keeping the ball at the center of the stream. That's one kind of classic demonstration of the Bernoulli equation. See if you move it over fairly significantly before I think it goes too far. No. Very good. So I'm going to take a heavier ball. It doesn't go up as far, right? But it's still held within that low pressure zone within the fluid stream. So here's another example where we can use the air alone in order to pull these two things together. Over time. But again, what's going on here is the fluid stream coming out of the straw at high velocity That therefore results in decreased pressure, and that's actually, well, actually it's the increased pressure, the atmospheric pressure on the outside of the cans, then that's pushing them inwards against that. Say that they're being sucked inwards by that decreased pressure. So we know that the pressure exterior to these cans is higher, and therefore really pushing pressure externally. So we need to really to understand these kind of like movement tricks, but we can also use this kind of a trick in real life devices. So a good example would be a carburetor. Right, so a carburetor is like the old school way of getting fuel into a different combustion engine, right? Cars nowadays don't have carburetors. We have fuel injectors. You can put in very precise amounts of fuel into an engine, so they don't waste quite as much, or just not much. But a carburetor is a really very simple device to get fuel into an engine. We'll look at how it works, but here's a basic like transparent version of one. Where basically we have air intake into the engine, which goes through this constriction here, and what we call a venturi. And then underneath it is a fuel reservoir area where we can add that. And now what's going to happen here is that if we have air coming in, right, through this region, as we decrease the size of the area, what happens to the velocity of the airflow? It goes up. By mass conservation, we know for an incompressible fluid, we're going to assume air is incompressible. The velocity of that fluid is going to go up when we decrease the area. Right. Remember, for an incompressible fluid, we would say that that's V1 A1 is equal to V2 A2. So if A2 goes down, V2 goes up. Right. So velocity here is higher. And now what does Bernoulli tell us? When the velocity is higher, what happens to the pressure? It's down. Right. We're in the region of low pressure here at the center of the venturi. And then there's a little tube to barely maybe make out sitting in the front. But there's a tube running down this reservoir down below. And so with this low pressure, it actually can pull the gas up into this region here. It forms this little atom hydrolysis, which is a substance. So watch this in action.
So the two components of the carburetor, right? Okay, first let's talk about the venturi. If you are like me and you have really old books on your shelf, you might have one that explains carburetors in great detail and explains that a venturi is a really cool thing where you take fluid that's flowing through a pipe. If you neck it down at some point to a smaller cross-sectional area, the static pressure at that point at the throat decreases, creating kind of like a vacuum in that one spot. Well, that can be used to suck fuel up into the venturi. All right, so let's look at that. So the venturi part of the carburetor is for sucking the fuel up into the line. The second part of the carburetor, the bowl, is for holding the fuel. So after a lot of
so I just want to come back to you for a second. So we now have for an explanation of what the venturi does. And we're visualizing the pressure, in this case, using manometers, right? Like our fluid static stacker. So the way we're going to read these, we're going to actually see two different types of manometers explaining what's going on in the venturi. So in this case, the end here of each of these manometers is open to atmospheric pressure. And so we know that the fluid surface, right, at the end that's open is at atmospheric pressure. So in each one of these, the pressure right here is atmospheric pressure. Then now the pressure where we have delta P is minus gamma delta C, right? So as we increase in height within a connected fluid, decrease in negative pressure, negative would be increase our pressure. And so we can see we have so the height of this inner surface of the manometer fluid above this region here indicates that the pressure is lower than atmospheric pressure. The higher this delta H is, the lower the pressure is at that region of the mature. And so we can see that in the center region here, we have a larger delta H, and therefore we have a lower pressure at this center, at this neck of the venturi than we do at either the inlet or the outlet. That makes sense? Right from our fluid status, right? So yeah, so just thinking it through, we know it's open end, so we know this is atmospheric pressure. Pressure goes up, down the fluid, and we can make horizontal jumps within connected fluids. We can jump over from here to here. And we know therefore that the pressure at this point, is higher than the pressure at this point. So the height of this tells us about the pressure at that point of the tube, the higher this is, the lower. Okay. So this is showing us the pressure is lower at the center, as you would expect from. I think it's kind of cool to see one of these in action. So we're going to watch the high-speed video from this clip. The whole clip is like 25 minutes long, so I want to encourage you to watch it. So along with the flow through this area tape, there's also a valve which is opening and closing in time when the engine is delivered. And when that valve opens, it basically allows the gasoline to come in through this tube into the center of that maturity. But you can see that when that valve is open, when that valve is open, we have the gas basically forced up this tube by the pressure difference between the reservoir below and the maturity neck above, and we have this gas being pulled in and atomized into those small particles as well. Okay, so so we can use the Bernoulli equation to understand what's going on in some toy examples, right? With the guy making a funny face, blowing air through a straw, the two cans together. Not very practical. We can also use the Bernoulli equation to understand what's going on here, right? And this is the basis for fuel injector. I do want to talk a little bit about limitation before we go to another example of the Bernoulli equation. I do want to talk about a limitation of Bernoulli related to a venturi. So if we look at this textbook example of load through a venturi tube, we'll see that in the textbook example we have the pressure decreases as we move to the neck, and then increases again as we come out the other side. And we see that that pressure has increased again to the same pressure that it was at the same area at the end. But in a real venturi, this doesn't exactly happen. So let's look at a real venturi, one that's not designed terribly well, but does illustrate the point. We'll talk about the design of the venturi in a second as well. But let's just watch what happens here. So this is now going to have in this demo we have this air flowing through the venturi from right to left, so we have the opposite of the convention that we do. This venturi is basically just a piece of glass tube that's symmetrically necked down into this little region in the center. And beneath it, we have another type of manometer we're going to have to talk about. But let's look at this. Let's watch the demo.
This is a venturi tube. I've got a source of air that will come in to this side of the tube. It'll pass through this region where the tube is wide, and then here where the tube is quite narrow, and then back to wide again. Since the same amount of air has to pass through this wide cross section as passes through here, namely the volumetric flow rate has to be the same, the number of cubic centimeters per second passing this spot has to be the same as the volumetric flow rate that passes this spot. And because this spot has a smaller cross-sectional area, the air has to flow faster here. So we've got a high velocity region here, a low velocity region here. But Bernoulli's principle says that the higher the velocity, the lower the pressure. So in this spot here, contrary to what your intuition might say, instead of the pressure being high here, the pressure is actually low. And we can demonstrate that using this colored water. I filled the bottom of these U-shaped glass tubing with water that has a bit of food coloring added to it. What you'll see is when we turn on the air, this column of water in the middle will rise because the pressure here is lower, essentially acts as a suction for the water. So this one will rise higher than either of the other two.
So we can see that column of water does indeed rise higher in the center, right? Indicating that the pressure is lower at the center of the tube as we expect from the liquid, right? But let's talk about what's happening here. So you'll notice that they're not the same. Now they could be not the same height because it's not the same velocity, right? That would explain it totally using the are these the same velocity? Is the air there? Is the velocity here there? Who thinks that they are the same velocity? Is the velocity of the air at this point the same as the velocity of the air at that point? Raise your hands for yes. Okay, two brave souls. Pretty brave souls. Raise your hands for no. Okay, and I see a lot of people don't answer. But so someone who said yes, why is that true? Why was that true? The area is the same and mass is conserved, right? The area is the same, mass is conserved, and we're assuming but so if we have an incompressible fluid, right? We have BA, it's B1A1 is equal to B2A. So this is section 1, and it has area A1, which is the same as our area A2, and that tells us that V1 is equal to V2. So these velocities are the same. Yeah.
Well, wouldn't it lose some kinetic energy friction? So technically the velocity would go down despite.
Question is, wouldn't it lose some kinetic energy friction? It will lose some energy. But by mass conservation, the velocity has to be the same. So it cannot lose kinetic energy. That energy comes from someplace else.
Okay, the water seems like smaller area of so the water
So could the water be evaporated a tiny bit and there would be more mass? I think the water is going to be evaporated a tiny bit. That will be negligible. This is not a mass balance problem. This is not a mass balance problem. It does have to do with energy loss. Okay, so the velocity here is the same as the velocity here. And so if we just have the Bernoulli equation, right? The Bernoulli equation for all that matter, then we're going to have P over rho plus 1/2 B squared plus G Z 1 is equal to P over rho plus 1/2 B squared plus G Z 2. Right. And they're both the same Z. And so you would predict solely from Bernoulli equation that this manometer should be at the same height, right? Between these two velocities. But we also have some loss to friction. in this. Right, so there is in fact some energy going into friction. That gets into the design of the Bernoulli. So this Bernoulli being symmetric is kind of a poor design for this kind of a contraction. If we go back to the textbook, you can see like this very asymmetric design. It comes out of the same area, but we have this rapid netting followed by this big gradual expansion. That's actually the limit frictional loss. It's kind of the standard design of a Venturi. And that's the design of a Venturi to limit frictional losses. In this example video, the Venturi hasn't been designed to limit frictional losses. We actually have pretty substantial frictional losses. And so if we write out the energy balance form of this, but there's no heat for work, but there is a head loss in friction. Okay. And so between section 1 and 2, we make the inlet section 1, the outlet here section 2. We know that the V1 is equal to V2, so these actually drop out. So this head loss, the frictional loss, is this is head loss here friction is kind of but this frictional loss is going to be balanced out by a loss of pressure. We have to lose the pressure plus the effect of pressure. This is going to be a common feature of pipe flow. So when we're talking about flow within a pipe, we're going to have a substantial frictional losses within that pipe. Typically, we're considering a long run of pipe. The area is the same. So by mass conservation, the velocity for that whole long run of pipe has to be the same by mass conservation. So what's where that energy is coming from, basically, where that energy is, where that energy is coming from. Pressure. Okay. So so this system demonstrates one of the limitations, which is that if we have 10 frictional losses, then Bernoulli equation no longer holds and would be strength. Yeah.
Does that mean that pipe flowing where you have a
So yes, so the question is, you have to keep increasing the pressure. At steady state, the amount of energy that you're putting in, so let's say by a pump, right? The amount of energy that you're putting in a big long run of pipe here right in front of the roof. And I'm running it until it's steady state. The amount of energy that I put in with a pump at one end to the creating flow would be exactly balanced out by the energy that I'm losing for the pressure, that I'm losing creating a pressure. Yes.
So in other situations, I don't know this actually makes sense now. Like, is that throttle and how like it's smaller again? If it kept getting smaller and smaller and smaller, eventually like back up the system where like the fluid can't get through. Like, I mean, it should be able to, but like in real life, would it actually like make the tank go through? Or
So what happens? So you're talking chapter 9 stuff. So is I continue to make the area smaller and smaller and smaller and smaller. What happens to the velocity? It goes high, right? And now this is, we said this is air, and I said we have to assume it's control. So what's going to happen at some point, as I make that area smaller and smaller and smaller, what's going to happen? Something critical will happen. It's going to become compressible across the center. Right, but at some points, we get accelerated fluid so much through that friction that it crosses the speed of sound. When we do that, for now we're going to sit here and take out. We're going to talk about those three things in chapter 9. But one of them, right, is that so the speed of sound, the velocity with the pressure wave travels in the air, right? So the velocity with pressure waves coming out right now are coming forward. So if you have something that's traveling at the speed of sound or faster, then basically what happens is that the air can't get out of its own way, not what causes the pressure. So you're correct. At some points, it will be like the air can't get out of its own way. But you have to get close to the speed of sound for that.
So this is probably still like future chapter stuff. If you're addressing how it came up, when we were doing the situation, will we have to account for whether the pressure difference in the atmosphere and the increase the pressure at the high velocity because of the collapse in the, like the pipe or whatever, it's cool that it's surrounding it.
So you're at, so at some point, yes, at some point the pressure would cause mechanical stress within the pipe.
Right.
We very briefly will talk about the strength required pipe systems, and like what. There's some pipe that should be like schedule 40 or schedule 80, pipe that has to do with basically the strength of the pipe they use. The ability to withstand pressure. We'll talk a little bit about that, we won't go into great depth on that on the mechanical, like straight side.
Is there enough to go over that, or does that be more like a graph?
I'm not sure what that would be. So to really understand what's going on with the stress and pipe, that would be mechanics of materials.
Okay.
Regular all mechanics class. Critical and failure would be. We will talk a little bit about the critical pressure of pipe. In a grad class, I'm not even doing it. It's not me. Grad food. Okay. Yeah.
We need that to the material.
Yeah, maybe. Okay. So again, the real equation can help us understand what's going on here, right? But it can only go so far in the face of frictional loss. I will say this is at Venturi again, this is kind of a poorly designed picture. So we are losing a lot of energy friction because of the shape of this. In a well-designed Venturi, these two liquid levels will be very close. Frictional loss generally. But in this case, CF is substantially. Just very briefly, again, we have a manometer here, right? In this case, the manometer is connected among all three fluids. So this allows us very directly compare among all three fluids. So we know that pressure goes up if we move down in the fluid. So that means that pressure down here, right, is higher, right? The pressure of the surface is higher than the pressure here. The pressure of that segment of the pipe is higher. And again, if we compare the inlet and outlet, again, we're going to see we have a higher pressure at the inlet than we do at the outlet. Like about. Any questions on this? Right, I just want to run way long on videos today, if that's okay. We're another way of using the Bernoulli equation to understand some real interesting physics is by looking at light. And so this is an example of putting spin on a ball, which has some deep connections to how airplane wings work. But let's just look at how we use Bernoulli to understand flow around for what happens to the spinning ball.
They drop a basketball over the edge. You can see that the basketball gets pushed around a bit by the breeze, but it lands basically right below where it was dropped.
So it's a basketball that's dropped with no spin whatsoever.
Now watch what happens when they drop another basketball, this time with a bit of backspin. Whoa, look at that go!
Super basketball, when it drops a bit of spin, actually curves out. There are a couple different ways of understanding this, but one way involves Bernoulli. So we imagine that we have the next side of the, you see me over here. Okay. So we imagine now we have a ball, and that ball is spinning, right? So we're throwing some backspin. We have it coming into oncoming air like this. Right? At the upper surface of the ball, the ball is going to be dragging the air backwards, adding to this oncoming velocity. And we'll end up with a large velocity at the top. At the bottom surface here, right, the ball is moving opposite the oncoming airflow. And so it's going to be opposing this airflow. And it's going to result in a lower velocity at the bottom. So by the Bernoulli equation, think of this as right, this higher velocity is going to result in a lower pressure top. Right, so we're going to end up with low pressure top, and the lower velocity means we're going to have a relatively higher pressure at the bottom. And the net result of this will be a net pressure force that pulls the ball up. So this rotation can actually cause this whole thing. So we can use this to make something fly. So this is a airplane of sorts. And it's basically like testing this principle. It's like, oh yeah, sure, this is going to work. So these are going to be back spinning differential buttons. That's driven by a motor on what otherwise looks like a normal kind of electric plane. And we're going to watch the thing fly. And go. Not the most elegant plane in the world, but it does work. It eventually crashes. But the principle holds, right? We can use this like backspin thing to make a basketball do something crazy off the dam. We can also use it to make something actually fly. Airplane wing is basically the same, or a sailboat sail is the same thing as airplane wing. But just sticking straight up instead of sticking out sideways. And so this kind of idea has actually been proposed to be used as something like a sail on a big ship, where you have a big rotor that spins, and use that to create a lift force that can actually drive boats forward. Potentially it's a way to offset fuel costs by having large container ships sailing basically. And we'll come back to the very end of class. This has some really deep relation to how a real airplane works and how a real airplane works. That idea and it's not learned about it. So sorry, I can't hear you. This Casey. Yeah. The reason why we changed the spin. It's full, right? But the spin is helping keep it stable, right? Like a gyroscopic force, but the shape is actually and allowing it to float. Okay, any other questions? Okay. Great. So let's get back to it. Back to the map. As a reminder, we were talking about Lagrangian versus Eulerian coordinates within a fluid, right? At the end of last class. And we said that we had developed an expression for the acceleration of a fluid particle, at least the x component of the acceleration of the fluid particle given by this, right? Where the total derivative, we said the acceleration of the fluid particle in the x direction, the total derivative of the u velocity with respect to time, has different components. One, which is just the rate of change of the velocity with respect to time, or the partial derivative of u with respect to time. And then it has these other components that depend upon the velocity of the fluid. Now we will typically define an operator, this del operator, as b dot del is equal to this expression here. Right, so basically encapsulating all of the right, the b u dx plus u dx plus v dy w dt. And this allows simplified expression. So we can now, for vector acceleration, or the total acceleration of the particle, we can write out this way, or simplify it using this operator as partial v partial t plus v dot del v. This is the acceleration of a fluid particle. And we typically will talk about this as having kind of two components. One which would be like the local derivative, so the rate of change of velocity at a given point, the partial derivative of the with respect to t. In steady flow, so if we have steady state conditions, the partial derivatives with respect to t of 0, make this term is 0, steady state. And then we have this term here, which we call sometimes the convective derivative. It has to do with motion of the fluid. And this is not necessarily 0 steady flow. Meaning that if we remember this term here represents the acceleration of a particle of fluid that's moving through some kind of system. And what this expression is telling us is that for that particle, it can experience an acceleration even if the overall flow system is at steady state. The example is here. So if we have, so an example is here. So we have flow through, like let's say this starts with maturity, right? And we're at steady state, and we're moving from a region of high area to a region of low area. Steady state means the partial derivative with respect to time is 0. Right, so flowing in this system in a lab frame, as I'm sitting here looking at it, is unchanging. But if I'm sitting on a particle, right, if I'm living within a fluid particle and I'm being swept through this system, I will experience an acceleration as I move from this region of large area to this region of small area, right? My velocity changes, therefore that particle has to accelerate. And that's captured by this term here, this convective derivative term here, captures the acceleration of fluid particles even in a steady flow. It's kind of a weird concept. Okay. So this derivative is sometimes called this total derivative. Sometimes it's called the substantial or material derivative. Also sometimes written with uppercase D, uppercase DT, instead of just the non-script D that your textbook uses. So and this describes the acceleration, the derivative of a property with respect to a fluid particle. Right. So we looked at dV dt, which was the acceleration of a fluid particle. But in general, we can apply this operator to other properties of the fluid in order to understand how they're changing within fluid particles, right? Parcels of fluid that are moving through our system. And so this total derivative describes the rate of change within a particle as it moves through the flow. We're going to use this to derive mass concentration. So if we apply this to the operator of density of a fluid particle, we have d rho dt, or uppercase d rho dt, right? The total derivative of density with respect to time. So now again, density of that fluid particle, we'll say has two components: the rate of change of density within that particle, within the fluid contained within that particle itself, plus the convective derivative, right? This thing that has to do with the flow. right, that the fluid particles. Yes.
You elaborate on how.
Yes, that's actually the slide after next, but, so to derive mass concentration, we're gonna say that the, total rate of change, total derivative of density with respect to time within a fluid particle is 0. So we're gonna say, static density is 0 is mass concentration, and therefore, and that's how we're gonna develop it.
In fluid accelerates, I think those two models, there has to be a force supply, right?
Fluid accelerators will have to be able to, so where does that come from? We're gonna talk about that when we develop the momentum balance in for a fluid particle. So we develop momentum balance for a fluid particle, yeah, so we're gonna use the same expression. So you guys are just jumping away, so we're gonna say, the derivative of rho v with respect to time, right, would be the rate of change of momentum of a fluid particle. The only way you can change momentum is by doing what? We're change momentum of a fluid particle is by velocity. Changing its velocity needs for changing momentum, but in order to do so, we apply it, right? So we're going to say that the rate of change of momentum with respect to time is going to be the applied force, and that's how we're going to develop the momentum equation, which is going to be able to have force. Yeah. Yeah, so this is saying this is the Lagrangian change of density, right? And Lagrangian means the change in density as we follow a fluid particle. So if we're living on a fluid particle, this is the rate of change in density that we experience. So this is the Lagrangian. And this actually is relating Lagrangian to polarity. So this is the rate of change that we would see at a given point sitting there at a fixed point. Be this rate of change. Partial growth. This is actually relating Lagrangian. Okay, so since we spent some time on videos, I don't think we're going to do this as an exercise right now in class. But we're going to we'll go through this. Let's say we have a velocity field, right, given in x, y, and z coordinates, indicated by those substituted by those unit vectors I, j, and k. And we can ask, is this flow steady, and what's the x component of the particle acceleration for this velocity? So by looking at this, so steady state means partial derivative of velocity with respect to time is 0. So is this flow steady? Anyone tell me if this flow is steady? There's something about T. Yeah.
Yes, there's no T.
There's no T component. So when I take the partial derivative of this expression with respect to time, it's just going to be 0, right? Meaning that the flow is steady. That it's a steady state flow. But now if I ask, now the second part here is what is the x component of a particle's acceleration? Right, so first part, we're going to check partial derivative of v with respect to t is 0. Is that true? And the answer is yes. There's no dependence on t, right? So we take the partial derivative with respect to t, we're going to see just get 0. Second is what is the acceleration of a fluid particle? Right here I'm looking for the x component. So this would be the total acceleration, x, y, and z would be the total derivative of velocity with respect to time. So my ax, right, I can expand this out using the definition of this operator from the previous slide. Partial u partial t, 0, plus u partial u partial x, u partial u partial y, w partial u partial t. Okay. Pay attention to where the u's and d's and w's are in this expression. That's the major place you can get to the company. When we work the problems like this. And when we work all of this out, we have 8x the acceleration from a fluid particle in x. Okay. There will be a problem like this. There is a problem like this on Wednesday. So I know we didn't cover it by Wednesday, but I want to make sure you have some practice on this for the exam. It's one of the concepts that I want to teach. So there is something like this on the Similarly, you find AY and AC by following similar kind of laws. So a way to test your understanding of this would be, can you get the same answer? And we can write this out as full vector acceleration having ijk components here. Multiply by, sorry. So that was, let's see, so B was 2xc multiplied by du, partial u, partial y, which is 4. Okay, so that was 2xc times 4. So for mass conservation, we are going to consider fluxes through small control volumes. All right, so we're going to basically start. We're going to derive our differential equations by looking at control volume. We're assuming you have some control volume there. It has size dx, dy, dt. And we're going to say that if the control volume is small enough, so even if we have some crazy distribution of velocity within our fluid, if the control volume is small enough, then we have approximately 1 d flow through every phase. And so we can use the one-dimensional form of mass conservation from last chapter to get started on this experiment. Right, so the rate of change of density within the control volume, plus whatever's going out minus whatever's coming in is 0. The volume is small enough that this integral we can simplify. It's just basically multiplying by dx and y. We're going to start in the x direction. So at the inlet we have rho VA, so that's rho times u, right, the exponent of velocity, times the area, which is dy dt. At the outlet, rho VA, right, the mass flux flow out, is going to be the velocity of the outlet. Now, rho u plus the change across that dx times the area. We'll do y and t. We're going to plug this in and see what happens. So we had our this was what the integral within the control volume of the rate of change in time resolved to. This is our outflow in x. This is our inflow in x. You notice we have this rho u. Sorry, this should be rho u times. Yeah, sorry, we have rho u dy dt minus rho u dy dt. Those terms are going to cancel out. And I'm just going to be left with this term that has to do with the derivative. And so I'm going to end up with this term for x, and I'm going to do the same for y and z. Same thing is going to happen. So I end up with this expression here. But now, if you notice, we have dx, dy, dt times everything. So again, that dx, dy, dt all is 0. So we divide through by dx, dy, dt. Okay, so all those terms cancel out. And what we're left with is the equation of continuity or mass conservation. It says, right, we have rho dt plus dx rho u, dy rho v, plus dt rho w. This is a general statement of mass conservation. I have not assumed that the fluid is incompressible. So this works for compressible fluids. We're dealing with compressible fluids later and understanding what happens. We take a Venturi all the way down to the limit of compressible flow. We can use this expression. It also works for steady or unsteady flow. Right, so we still have that particle growth particle. We haven't said anything about whether or not the fluid is Newtonian. We haven't said anything about, the effects of viscosity here. This is a pretty general statement of mass concentration. We can simplify this using the gradient operator, which we used previously to define, simplify, our total derivative term. We'll get rho dt plus del dot rho v equals 0. And in this form, we can actually write this out for cylindrical or spherical coordinates. One last concept that I just want to put on your plate, but we're going to revisit on Monday, because I know we're going to have right now, is what happens if we have a special case of incompressible flows. Does come up on that homework. So in incompressible flow, rather, the density is constant. So take this term here, partial rho, partial t is constant. The rho comes out of this derivative operator. And we're left with this expression. So this is the expression of mass conservation for an incompressible fluid. Big box around it. When we're talking about incompressible fluids, this is going to be what we're using to define mass conservation. We're going to talk more about the weirdness of this, how to use this, and so on Monday. But this is something you're going to need to use on the course. Next. All right. Thank you all. Have a great weekend, and I'll see you on Monday.